So causal models are at the heart of this book. We introduce them in chapters 2 and 3. We go into a lot of detail about what DAGs, directed acyclic graphs, are and how they fit into this larger structure of causal models. In doing that, we are drawing on a large literature that, at the center of which is the work of Judea Pearl and many of his collaborators. We're sort of importing that framework and building on it. In this video, what we want to do is provide you with a few key takeaways that you should be keeping your eye on as you read chapters 2 and 3.
Great. So we're going to start by looking at a DAG and seeing what information it encodes and what it doesn't encode. So here's an example of a DAG that it's one that we explore in quite a bit of detail in the book. It's meant to capture relationships between inequality and democratization. So the idea is that democratization or democracy is the outcome variable we're trying to explain, and inequality is the cause of interest. Okay? So this DAG has got actually 4 different nodes here, nodes of variables. We've got I for inequality, we've got D for democratization, we've got M, which is mobilization, and we've got P, which is for pressure, external pressure. And the arrows in this DAG are trying to capture the idea that I might directly affect D, so inequality might lead to democratization directly in some way, or possibly I might affect M, I might affect mobilization, and mobilization in turn affects democracy, right? And while all that's going on, you might also have this other thing, P, pressure, that is separately possibly affecting democratization. Okay, so that's the core thing, is capturing a set of theories that we have in the literature, but the core thing we have to capture those ideas in this DAG are the set of nodes we care about, the set of variables, PIMD here, and the set of arrows, which are saying which ones are causally affected by which other ones.
There's some information conveyed in the DAG about our beliefs about the world, but I think is readily apparent, there are certain things that the DAG doesn't tell us about causal relations, right? So for instance, inequality to mobilization link, what the DAG is not telling us is whether that's a positive effect of inequality and mobilization or a negative effect.
Actually, a lot of people assume when they see a DAG, they're thinking that this means a positive relationship, right? Could it just as well be a negative relationship?
That's right. It could be positive or negative. And likewise, where we've got, say, both mobilization and international pressure affecting democratization, the DAG isn't telling us what form that sort of joint causation is taking. It doesn't tell us whether it's an additive effect or an interaction, or if it's an interaction, is one amplifying the other or dampening it? The content of those causal relations, they are not represented in the DAG.
Yeah, that's right. So people often find that frustrating. And what I've often seen is when people want to capture the idea that one variable moderates or affects the effect of another variable. So for example, that the effect of mobilization is different when there's more or less pressure, is they try and draw an arrow from the P down towards the MD arrow.
Like this,
exactly,
right?
Do it like that. And that's meant to capture that kind of intuition. But that's actually kind of out of sync with the idea of DAGs, because the key idea in the DAG is we want to know which variables cause other variables. Which ones have effects on other variables? And the arrows themselves are capturing the idea that there is a relationship, right? But it doesn't say anything quantitatively about what that relationship is.
And so as you're probably kind of getting a sense of, while DAGs are arrow diagrams, they're arrow diagrams with rules, with a grammar. And let's just say a little bit more about what that grammar is. So one important sort of concept in chapter 2 is the difference between including an arrow and excluding an arrow. So when we include an arrow, like the arrow from I to M, what we're saying is inequality might have an effect on mobilization. We're allowing for the possibility of a direct effect, and that's important. We're saying not through some other variable in the model, but directly inequality might affect mobilization. But when we include the arrow, we're not saying it definitely has that effect. We're not saying it always has an effect. We're just saying we're allowing for the possibility that it might have that effect. Now, on the other hand, between any 2 nodes, when we do not have an arrow connecting them, we're making a much stronger statement in the other direction. we're saying there definitely is not an effect. We're prohibiting, essentially, an effect, a direct effect between those two. So for instance, here, there is no arrow from P to M, right? What we're saying with that is we're making a strong claim that external pressure itself does not have an effect, does not have a direct effect on mass mobilization. Likewise, there's no P to I arrow. We're saying external pressure does not have an effect on inequality, right, in this world. We can look at a somewhat more subtle version of that in this next graph. So here, what we've done is we've taken away the arrow from I to D. And here we need to think about the difference between direct effects and indirect effects. So in taking away the I to D arrow, we're saying there is no direct effect of inequality on democratization. Now, as you'll notice, there is still a way for inequality to affect democratization in this model, right? Through mass mobilization. So that's fine. There still is that indirect effect that's captured by the model. But we're saying, essentially, if inequality is going to have an effect on democratization in this model, it has to go through M. It has to go through mass mobilization.
Yeah. And a subtle idea that's conveyed there is that there's a type of independence between I and D conditional upon M, right? When you say that the effect of I on D has to go through M, what you're actually saying is, if you were able to keep M fixed, right, M doesn't change, then I won't affect D. And actually, slightly more strongly, you don't even expect any kind of statistical relationship between I and D if you keep M fixed, right? That's going to become very important for us later. It turns out that I is not going to be informative about D if you know M or if M is fixed, right? At least if this is the right DAG.
Let's talk about one more sort of feature of DAG, sort of in the standard version of DAGs. So let's think about confounding. So sometimes we think that there's some third variable that affects two other variables that we're interested in. If we know what that third variable is, then we include it in the DAG, right? We actually make it a node in the DAG and we draw those arrows. In other situations, we think there might be confounding by some variable or set of variables, but we don't know what that variable or what those variables are, right? And so that's what we call unobserved confounding. And when we are in a situation where our prior knowledge or beliefs don't allow us to rule out unobserved confounding between two variables, we want to represent that as well. We want to capture that. And the way that we do it is with this double-headed arrow. So if you look at the double-headed sort of curved arrow between P and M, what we're saying there is we're allowing for the possibility that the kinds of states that tend to have mass mobilization are also the kinds of, that a state's tendency to have mass mobilization is correlated in some way with its tendency to be an object of international pressure. Right? We don't know why, right? We can't specify what the third variable is, but we're allowing for that kind of confounding. And by the same token, in the previous version, going back here, where we don't have that double-headed arrow, again, that's a missing arrow in a sense. It's an arrow that we're not including, and we're making a strong statement there. We're saying that we believe there is no confounding between M and P, right? Or really between any two variables in this particular model.
Yeah, that's great. So what we've seen here is the DAG contains a lot of information. It identifies what are the key causes we care about. It identifies which ones possibly relate to which, and it says a lot about the possible statistical patterns that are consistent with the world as we're imagining it, or would be inconsistent. But for all that, it doesn't answer basic questions. It doesn't answer, as we said, questions about whether an effect is positive, whether an effect is working through one channel more than through another channel, or anything of that form. And so to answer those kinds of questions, we have to think through some way to augment the DAG to capture how things are related to each other and not just whether things are related to each other. That's what we're going to look at next.
So let's take sort of the world's simplest DAG. We've got two nodes. X and Y, an arrow from X to Y, telling us that X might have an effect on Y. Okay, so this doesn't, as McCartan was saying, this DAG doesn't tell us whether that's a positive effect, negative effect, or no effect at all, potentially. We're going to layer something onto that. We're going to layer on a theta node. You're going to see a lot of theta nodes in this book. So what a theta node is think of it as like a receptacle for information about what kind of an effect one variable has on another. So here, this theta y is what we're going to call y's nodal type. It is basically, theta y captures the kind of effect that x has on y. Now, throughout the book, for reasons of sort of simplifying the exposition, and also it simplifies computation, we deal with we treat all nodes basically as binary, as 0 or 1, not a necessary feature of using the approach, but that's how we're going to sort of work through things. So if you've got just binary nodes, one pointing into the other, there are only 4 possible kinds of effects. These are our 4 types that we introduce in chapter 2. So X can have a positive effect on Y, X can have a negative effect on Y. There could be no effect with Y always 0, or no effect with Y always 1. That's it. There are 4 possible types, 4 possible effects. Theta Y, for a given case, takes on one of those 4 values, right? So theta Y could take on, for a given case, a value in which X has a positive effect on Y. For a different case, it might take on a value such that X has a negative effect on Y.
Yeah, I think maybe a subtlety is that theta y is capturing not just the level of some node, but it's capturing counterfactual possibilities, right? It's capturing, when you look at x or y, you can imagine measuring those. You can see what x is, you can see what y is. Theta y is something you're not going to observe, but it says not just what y is given x, it says what y would be given different possible values of x. Right. So it turns out that's the quantity that characterizes the causal relationships. That's what we want to understand if we want to understand causal relationships in this graph.
And again, we are thinking here very much at the case level, right? We're thinking about each case as having a type, right, for each node. And there are more complicated versions of this that you'll see in the book. So here we've got 2 variables, x1 and x2, both pointing into y. Theta y is essentially the same kind of thing. It is the receptacle for the type that the case is in terms of how y is responding jointly to these 2 causal variables, x1 and x2. Now, there were only 4 types when we had 1 variable pointing into y. The bad news here is that the number of types increases quite rapidly as the number of causal variables pointing into some outcome increases. So here, with 2 causal variables pointing into y, we've got 16 types instead of 4. But those types, they capture all the possible ways in which x1 and x2 might jointly affect y. So, the possibility that x1 has a positive effect on y all the time, the possibility that x1 has a positive effect on y only when x2 is 0, or only when x2 is 1, right? All those possible permutations, there are 16 of them. And for each case, again, each case is going to be of one of those types, one of those 16 types in terms of the counterfactual relations governing the joint effect of x1 and x2 on y.
Great. I think we have another example in the next slide.
Let's look at this.
So here's for a slightly more complex graph. Here it's a little bit similar to the democratization DAG we saw. Here x affects y. It might affect it directly or indirectly. And here you notice we've got a theta for all 3 nodes. We've got a theta for x, we've got a theta for m, we've got a theta for y. Those are nodal types for those 3 things. Theta x simply says is x a 0 or 1? It's a very simple one, right? Theta m is saying, how does m respond to x? Could be one of 4 types, positive, negative, no effects of different sorts. Or theta y, like we saw before, has got 16 possible types, right? Saying the different ways that x and m might combine to produce y, okay? Those are all the different nodal types. And what we're going to be calling the causal type is the collection of those nodal types. So a given unit will have a particular theta x, particular theta m, particular theta y. That's its causal type. And if you know its causal type, you know its values it takes on, and you also know what values it would take on given any possible interventions on x or on m.
So again, at each node, each case has a nodal type, and then the collection of nodal types that a case has are its causal type. All right, so we've been talking about cases and the types that they can take on. And a lot of the questions social scientists ask, particularly qualitative researchers, are about cases. And essentially, for reasons we'll get into, those in our framework are questions about the case's theta values. But a lot of questions we ask as social scientists are about populations. And so we need a way of situating the thetas, the cases, and their types within a larger population. And so for that, we layer on, we have an additional layer here that we can think of, that we represent as lambda. And essentially, the way to think about lambda is it is the distribution of nodal types in a population. Or we can think of it as essentially the proportion of a population that is of each nodal type. So, for instance, take the lambda x in the top left. That represents the proportion of cases in the population that are of each of the two theta x types. Mm-hmm. For what proportion of the population is x0? For what proportion of cases in the population is x1? Lambda m, which is above theta m, represents the proportion of cases in the population that take on each of the four theta m values. So for what proportion of cases in the population does x have a positive effect on m? For what proportion does x have a negative effect on m? And so on for each of the four types. Lambda y, as you might guess, is a vector representing the 16, the shares of a population taken on by each of the 16 types that theta y can represent.
Right. So when we're asking case level questions, we want to ask about the thetas. When we're asking population level questions, we want to ask about the lambdas. That sort of sets out the problem we have. Just to point out, it should be fairly obvious, we have a very difficult inferential problem here, in that when we go and look at the world, we can see x, we can see m, we can see y. We can't see theta x, we can't see theta m, we can't see theta y. And we certainly can't see lambda x, lambda m, or lambda y. Those are things that we're going to start making inferences about, right? So the question is, how are we going to make those inferences?
Well, we're going to get to that in the next video.